Hello and welcome, dear friends. We are now entering into a very new chapter, group theory and molecular orbital theory, particularly in context to the applications to delocalize patterns for organic molecules. Again, I'm your instructor Saurabh, and we are going to see the various aspects of theory. The molecular orbital theory for the pi molecular orbitals or conjugated system was developed by Huckel, and it is very popularly known as Huckel's theory. We'd first go to the fine details of the theory, and then in later sections we'll be talking about how this use of group theory and symmetry would be useful in solving various problems and in simplifying various calculations. Indeed, they are very useful for simplified calculations. Molecular orbitals spread over the entire molecule, as we know. Consideration of molecular symmetry, therefore, is very useful. And as I have mentioned earlier, that group theory reduces the computational work involved, and therefore it is quite useful. However, now because of the use of computers these days, this has got a less significance. But even then, it has been a theory of importance. To begin with the LCO method, we'll first take the linear combination of atomic orbitals for sigma or pi framework. We'll talk about for a diatomic molecule like hydrogen molecule ion and so on. For hydrogen molecule ion, because it provides a simplest case of 2 proton 1 electron system, the wave function psi can be written in its normalized form as C1 phi1 plus C2 phi2, where psi is an approximate wave function and phi1 and phi2 are the two wave functions of various atomic orbitals that combine to give this value, and C1 and C2 are the coefficients reflecting different contributions of two identical atomic orbitals described by phi1 and phi2. So phi1 and phi2 are used for atomic orbitals, and is of course the normalization constant. Now, to obtain the energy of any system, we must start with the principal Schrodinger wave equation and then minimizing it to get the best approximation. The simplest form of the Schrodinger wave equation is H psi is equal to E psi. You understand that H is the Hamiltonian operator, where the psi is the wave function of the molecular orbital. And if we multiply psi on either side and integrate it over the entire space, entire volume element, then what you get is psi h psi d tau integration of psi square d tau. D tau is known as the volume element, that is equivalent to dx, dy, dz. So we can even write three integrals, or rather one integrate is sufficient in this particular case, where you have d tau is equal to dx, dy and dz. That's also known as the volume element, because x into y into z refer to the volume also. Now, as we have seen that for a wave function psi, we can write it C1 phi1 plus C2 phi2. So what I have done in this equation, that we have substituted the values of psi for the linear combination of atomic orbitals. The concept is the atomic orbitals can be added or subtracted by the approach we call it LCA approach. So therefore, I have substituted the value of psi in terms of C1 phi1 plus C2 phi2 that has produced the result that has been shown in the equation number 2. Now, the rest of the thing is merely mathematical. Just keep on multiplying the components inside as described here, and you will reach to the final solution that is coming onto your screen. That is something like this, which is represented by equation number 3. Now, this particular equation demonstrates that here what we have done is we have simply multiplied the components including a Hamiltonian operator, and we are getting the value C1 square phi1 h phi2 d tau, C1 C2 phi1 h phi2 d tau, C2 C1 phi2 h phi1 d tau, C2 square integration of phi2 h phi2 d2, and so on. And so is the case with the denominator. And so therefore we have got this equation, and if we wish to further simplify it, what we can do is we can write phi1 square. Similarly, this is you have phi2 square and so on. Just the numerator that has not been changed so far in the equation, but we have made a slight difference in the denominator form. Well, if we use the abbreviations of the type that we have shown here, phi1 h phi1 d tau is equal to h11, integration of phi2 h phi2 d tau is h22, phi1 h phi2 as h12, and phi1 h phi2 as here the integration must be 2 and 1 respectively. So here it's 1 and 2 is okay, but here it must be 2, 1 is okay, here must be 2, and here it must be 1. Anyway, and similarly, if we assume that phi 1, phi 1 d tau, that is phi 1 square d tau is S11, phi 2 d tau is S22, phi 1, phi 2 d tau as S12. These are the abbreviations that were used by Huckel originally. They are also known as Huckel's approximation that we'll see later, the detailed concept. But then what we can generally assume is all those integrals which are of type phi I h phi j d tau can be named as hij, whereas all those integrals of the type phi I phi j d tau can be named as sij. So these are the abbreviations that we have been using or will be using in the rest of the literature for coming days. Now again, substituting phi 1 h phi 1, so for phi 1 h phi 1 what I have written is h11, similarly h12, similarly h21, similarly h22, s11, s12, s21 and s22. For denominator side we have been using the term s, and for numerator side we are using the term h, and various coefficients have been shown here. That's equal to numerator upon denominator for some reasons that we'll see right now. Now we'll have to assume that h, that is an Hamiltonian operator, is quite symmetric. That is h12 is equal to h21. In that case, c1, c2, and because they are constants, so c1, c2 and h12 will be equal to h12. So it becomes twice c1, c2, h12. So our equation is further reduced to 2c1, c2, h12. Rest of the things are same, c2 square h22, and here there is no problem because they are the eigen values. So c1 c2 is and c2 c1, that is c1 c2 and s12 is equal to s21. There is no difference into that. So c1 square s11 plus 2 c1 c2 s12 plus c2 square s22. Now that is again equal to numerator upon denominator. Now as far as the principles of Huckel approximations are concerned, we now choose such that the energy is minimum, and this is achieved by differentiation with respect to each of the coefficient in turn and equating it equal to 0. That is del E upon del C1 is equal to del E upon del C2. That should be equal to 0 according to the conditions of minimum energy. So we learn in differential calculus maxima and minima. So we have equation number 4 that has to be differentiated with respect to C1 and C2 respectively. Let us see how does it responds to differentiation with respect to C1. Now if you go for it, you have got this principal equation, and let us assume that this is equal to numerator upon denominator. And if we want to differentiate it, what we will do is we'll apply the formula of differentiation, saying that denominator is such a differentiation with respect to C1 for numerator minus numerator is such as such differentiation of denominator with respect to C1, and the square of denominator has been expressed in this. This is the actual formula for differentiation when we use the ratio or the quotients. For example, for a numerator and denominator, the formula is expressed as denominator square, denominator as such, differentiation of numerator minus numerator as such, differentiation of denominator, that all equal to 0. So here what we have done is in some cases we have differentiated the way we have shown, and when I take this C1 square S11 to C1 and take to the other side and multiply it with 0, the product is obviously going to be 0. So if I start with this and multiply it with 0, I get 0. So this term is automatically reduced and we are left with only this equation, that this is minus and so on. Now the next thing that we are going to do is the differentiation of the terms that have been shown here. So be ready for the differentiation because we are doing differentiation with respect to C1, and therefore you see for C1 square the differentiation becomes as 2C1, while for C1 here rest of the things are as such, they are assumed to be constant. The C1 is dropped to 1, so what is here is 2C2H12, and for C2 square H2, because this is a constant and the differentiation of a constant drops to 0, so therefore there is no term involved here. Similarly, in case of numerator, C1 squared goes to 2C1S11. Here C1 goes to 1, so what is left is 2C2S12, 2C2S12, and the third term is automatically drops to 0 because it is constant for that particular value, and the differentiation of a constant is always 0. So we have got this equation, and now what we are trying to do is we are placing or rather substituting the place of denominator here. So n upon d comes here and the rest of the things are as usual you have seen here, and because n upon d is nothing but energy, we have seen that n upon d is energy, so we'll substitute here that this all is equal to energy, and we'll take the appropriate things into common. So let's take 2 into common and cancel in on the both the sides. So what we have is something like this, and then you can be rearranging the components of coefficients C1 and C2 respectively together, so that you have equation like C1H11 minus EC1S11 plus C2H1S12, here must be H12 minus EC2S12, that is equal to 0, and then it ultimately goes to something like this: C1H11 minus EC1S11 plus C2H12 minus EC2S12 is equal to 0. Now take out the coefficients C1 and C2 in common, and we arrive at the equation C1H11 minus ES1S11 plus C2H12 minus ES12 is equal to 0. You know, C1 and C2s are constant, H11 are the integrals of the type psi phi I h phi j d tau, and S11 or S12 are the integrals of phi I phi j d tau in the entire space. This is the equation that we have received for differentiation with respect to C1 and substituting it equal to 0. If we proceed for the same procedure, if we go for the same procedure with respect to C2, the equation that we are going to get is of this kind, that is C2H21 minus ES21 plus C2H22 minus ES22 is equal to 0, and then these two equations, that is 5 and 6 equations, are nothing but a set of simultaneous equations, or which are also known as secular equations, and then the coefficients can be put into the form of a determinant, which is also known as a secular determinant. So what we have is H11 minus ES11, H12 minus ES12 here, then you have H21 minus ES21, H22 minus ES22 is equal to 0. Now this determinant that we have obtained is known as secular determinant, and this can be solved for the value of energy. That is the beauty of the entire expression that we did so far. This was for a system where the electrons were moving for around the influence of 2 nuclei. But if this is the case for n number of electrons revolving around the influence of n number of nuclei, then the expression can be further changed, or we can have a very generalized form of the secular determinant of the type is as this one: your H11 minus ES11, H12 minus ES12 dash 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 H1n minus ES11. Similarly, H21 minus ES21 goes to H2n minus ES2n, H31 and so on goes to H3n minus ES3n, H41, 42, etc. goes to 4n minus ES4n, and similarly it goes to Hn1 minus Esn1, Hn2 and so on, ultimately goes to Hn minus Esnn is equal to 0. Of course, that's the determinant order n into n. So all the times we did not construct a secular determinant or derive all the mathematics that we did so far. You know, depending upon the case, for example, if you are using for a 3-membered or 4-membered or 5-membered systems, then you can have secular determinants of order 3, 4 and 5 and so on, and solve it for the value of energy, and the rest can be done on that basis. So that's all for now. Thanks for watching this video. We'll be going ahead with the next videos, applications further using these videos for the conjugated systems. Thank you very much again.